In this video, we will talk about what critical numbers are and how to find them. So I want to begin with the definition, which says that a critical number of f, of some function f, is a number in the domain of f. So it has to be a number in the domain of our function, such that f prime of c is either equal to 0 or f prime of c is undefined. So it's a point where either the slope of my tangent line is 0 or the slope of my tangent line is undefined. So let's do an example. This says, let f of x be x to the 1/3 times 2x minus 5 to the 4th power. Let's find the critical numbers of f. All right, so I need to begin by taking the derivative. So for this derivative, I'll need product rule. And product rule says we'll take the first function, which is x to the 1/3, multiply it by the derivative of the second, and that requires chain rule. Chain rule will deal with the outside part, this 4th power, first. So I deal with that. The 4 comes down, and I'll subtract 1 from the power to get a 3. And when I do that, the inside stays the same as 2x minus 5. But then we do the chain rule step, and we multiply by the derivative of the inside, which is 2. Okay, so that was first times the derivative of the second. Then we get plus the second, 2x minus 5 to the 4th, times the derivative of the first. And the derivative of the first function is going to be 1/3 x to the negative 2/3. So that was just some power rule. Alrighty, and now I need to find critical numbers. So when I set this thing equal to 0, it'll be helpful to have it factored. Okay, so let's factor it. And when I look at this first term and I look at that second term, they have some things in common. So one of the things that they have in common is this 2x minus 5 to a power. I can factor out 2x minus 5 to the 3, because that's the smaller of these two powers. When we look at x to the 1/3 and x to the negative 2/3, if I use that same idea of factoring out the smaller power, I could factor out x to the negative 2/3, because that's the smaller of the powers. And now let's write what's left over. From the first term, 4 times 2, that'll give me 8. And then, let's see, we had this x to the 1/3, but now we factored out x to the negative 2/3, so I divide by that thing that I factored out, x to the negative 2/3. I'm really going to show my steps and how I simplify that, but you may have been able to work that out in your head for what we are left with when we factor out this x to the negative 2/3, and that's fine. Okay, and now let's go to the next term. So we'll have plus, there will be a 1/3 left over, and there will be a 2x minus 5 to the 1, so I can just write 2x minus 5. But the x to the negative 2/3, that is factored out already. Okay, so we have this x to the negative 2/3 times 2x minus 5 being cubed. And then in brackets, now we have 8. And then this x to the negative power, I can bring it to the numerator, and that'll become positive. So I got x to a 1/3 times x to the 2/3. So the powers are going to add, and that'll just give me x to the 1, which is x. Okay, so that's very nice. And then we'll have plus that 1/3, 2x minus 5. And then to be able to combine these, I'm going to go ahead and get a common denominator. I'll multiply the 8x by 3/3, and now I'll start to simplify. So simplifying this, we will get 24x over 3 plus 2x minus 5/3, and this will become 26x minus 5/3. All right, so overall, what we now have, I can start to write this as one fraction. So the 2x minus 5 cubed, I will write that where it is. This x to the negative 2/3, I'm going to bring it to the denominator. So it becomes x to the positive 2/3. The 3 in the denominator from this fraction, that will multiply the x to the 2/3. So I'll get 3 times x to the 2/3. And then the 26x minus 5, that'll be multiplying what I have on the numerator. 26x minus 5. Alrighty, so that, let me write that minus 5 better. That is our derivative, just simplified. Now we're ready to set this thing equal to 0 and figure out when it's undefined. So let's set it equal to 0 first. So if I were to set this equal to 0, I could multiply both sides by the denominator, and that would get rid of the denominator. And what I'd be left with is then just setting each of the terms on the top equal to 0. So essentially what we're recognizing is this is going to be equal to 0 when the numerator equals 0. And let's just write down when does the numerator equal 0. So from the first factor, that's going to happen when x is 5 over 2. And the second factor is going to be equal to 0 when x is 5 over 26. We also need to figure out when our derivative is undefined. So when is our derivative undefined? F prime of x is undefined. Now I need the denominator to be 0. That will make my fraction undefined. Denominator needs to be equal to 0, and that's going to happen when the x is 0. Okay, so we have these three x values. Some of these make the derivative equal 0. Some of these make the derivative undefined. I can't say that they're all critical numbers yet, because there's one condition I haven't checked. For something to be a critical number, it needs to be in the domain of the original function f. That is really important. So if I look at this original function f, I have to make sure that these values that I got, so which values did we get? We got 5 halves, 5 over 26, and 0. Do any of those make this function be undefined? Because maybe they make the denominator be 0. And the answer is no, none of them. They're all good. So all of these are in the domain of f. So this one is, as are both of these. Alrighty, so they are all going to be critical numbers. So our critical numbers are x equals 5 halves, x equals 5 over 26, and x equals 0. We have 3 of them. If any of these numbers were not in the domain of the original function when we plugged them in, they would not be critical numbers. Alrighty, so I want to end this video by stating a key theorem about critical numbers. And this theorem is called Fermat's theorem. So when I pronounce this name, we don't pronounce the T. So I just say Fermat's. Okay, and this theorem says that if f has a local max or a local min at x equals c, then I'm actually going to motivate this by going back to my graph from the previous video. So let's think about the places where our local maxes and local mins occurred. Well, at this point, -3, 5, our derivative was 0. This tangent line seems to be horizontal. At -2, 3, I seem to have a sharp corner, so my derivative is undefined. At 1, 4, our derivative is 0. And then the last local min, 3, 1, our derivative is undefined because our function is not even continuous there. So Fermat's theorem will say that, okay, at a point where I have a local max or a local min, then it has to be the case that our derivative will be equal to 0 or our derivative is undefined. And now we have a word to describe such points, i.e., that is, c is a critical number. But be very careful with this. The converse is not necessarily true. The converse would be if our derivative is 0 or our derivative is undefined, it's not necessarily the case that our function has to have a local max or a local min there, and we'll see a practice problem involving that in our discussion videos. So in terms of our goals for this section, we finished goal 2, finding the critical numbers of a function. We've also talked about Fermat's theorem, which is part of goal 3, but we'll see this other theorem called the extreme value theorem in the next video.